Oh, great. Today we are, let me just share slides as well. Give this one. Great. So do you see the slides now?
Yes.
Let me just. Great. So today we are talking about. Let me actually just use this one. That might be better for the presentation. Good. Do you hear me well?
Yeah, we can start.
Great. Okay. So today we are continuing. We talk about all, this problem that you could solve them in polynomial time. And then we talk about the NP hardness and the problem that we cannot solve them in polynomial time, at least as of now. The question is that for those problems that we can solve in polynomial time, especially due to current era of big data, we need to be able to solve them faster because these are large data, even linear, sometimes like quadratic running time that we have for some of these problems are not enough. And for some of these problems, we may need to answer the queries instantly or almost instantly, and for lots of users. So we need to have a faster algorithm. And of course, one idea is to use parallel algorithm. It means that if you have some task, you want to run it, just not one computer is working on it, lots of computers simultaneously are working on it. Today, I just want to give some introduction to this and the current, state of the art for this set of problems. Good. So as we discussed, there are datasets, huge datasets that needs to be processed. Usually we cannot even have everything on one machine. We need to have it on several machines. And particular modern parallel frameworks for this are MapReduce, Hadoop, and Spark. All of them are based on this new model that we call it massively parallel computations. So here, when we talk about the massively parallel computation, includes actually all of these guys as well. The idea is that we will distribute the workload into several machines, generally the data set, and then in parallel, we are solving all these problems. And one of the important problems that we are considering here is that what is the true computational power of these parallel systems? Still, we don't know about the answer. We have some results that exist, but several important open problems remains open. Good. So one particular thing that we have done, this was this graph. This is the NeurIPS 2017 paper. We have this paper about the affinity clustering. There is a Google research blog on that if you search about affinity hierarchical clustering. So one of the things that I was early works also in the area that we have done it at Google. And this, we could, it was actually amazing. We could cluster some graphs with 10 to the trillions of edges. We could do it only like less than a minute or so. We could cluster them. And that was amazing. And this was actually a sort of several works in this area as well. There were some works before, but this was one of them that was practically was very important problem. So this is about affinity clustering. There are lots of nowadays. This is the first paper probably that talks about this model of MapReduce. But since then, there are lots of things and lots of simplification and lots of papers to solve the problems. These are some of these things that you can look at it. Here, in this talk, I just want to give you some introductions into these problems. And the approach that we are using, in particular, if you want to use any of these new approaches of MapReduce, massively parallel computations, which also include Spark and Hadoop. So I want to talk about two important problems here. The first one is the maximal matching. I will define it. And this is the paper that we had it. The good thing is that these problems, actually the way that, like the algorithm is very simple to describe and the proof is not, but that's one of the places that actually it is very nice to have some nice algorithm that everyone understands. The proof might be a bit complicated. I will give you some ideas about it. That is for maximal matching, which is a very fundamental problem. Matching problem is very fundamental in all algorithms and all marketplaces. Like for anything like Uber has a marketplace that connects users to drivers. Amazon is the same. Essentially, the customers to sellers, and Google the same thing, advertisers to users. All of them have this matching problem in the background. And the other one is, which is very important, is about the edit distance. That also we will talk about how can we make it parallel, and just give you the ideas about the algorithms. This is from these two works. So these are two fundamental problems that I want to say how we can solve them using these frameworks. Good. So let's talk a little bit about the massively parallel computation model. So like in the graph problem, we talk about edit distance as well, but in the graph problem, you are given a graph G with n vertices and m edges, and say the maximum degree is delta. You have m machines, each with a space S. We are assuming that this n, or I mean the m input, you cannot put it all in one machine. So we assume that S is much smaller than m. Like m is the input, n vertices, m edges. So m can be large. We are assuming the space per machine is much smaller than m. So each machine can get only a subset of edges. And of course, we have this property that always we have this one, that S times m should be order m, or order input in general. So what does this say? It says that the number of machines times the memory per machine should be the input size. And that should be a natural constraint because you need to put the input on these machines. And the minimum number of machines that you need is the input over the number of machines, over the space per machine. Any questions so far? Good. Now, how do we do the computations? By the way, I want to also emphasize that this concept of parallel algorithm was there before, but generally before we assume that these computers are and still the people are considering that we have lots of CPUs, all of them the same shape, and that's the way that we are doing parallel algorithms. Nowadays, this massively parallel computation is more combination of distributed system, distributed computers, and parallel computation. So here, the computers, there is no need to be the same. They can be servers of different capabilities. And we have also this concept of virtualization, that actually one server can run several servers, the job of several servers. One strong server can do, job of several regular servers. So in some sense, this is not, these computers can be different and they are not all the same. That was done before. So in some sense, this massively parallel computation model, which is a very practical one nowadays, use almost everyone, especially Apache Spark that we talk about it, is the current state of the art and somehow resurrection of parallel algorithms that before assumed that all these computers are the same, but here is much more general. And they might be distributed. They are not all in the same place also, scattered over the whole board. Okay, now given this, and I mentioned these computers, here we have this kind of computers, just a space of these machines, which is important. And then that can be also different for different machines. Because as I mentioned, you can always, if you have a strong server, you can break it down into a smaller server thanks to virtualizations that we have. Anyhow, so but for this one, we are assuming that these machines have the same space. Now, computation proceeds in rounds. By the end of each round, so we have at the beginning, we are assuming somehow we read the data, and the data is somehow scattered on these machines. And then each, so now we are doing rounds, and at the end of each round, each machine can send and receive messages, total of S bits from, so it can send to other machines at most S bits and can receive the information from others at most S bits. So let's see this one. So these are the computers that we have. You can consider, as we discussed, this computer, typically, you can consider this is a cluster of computer. This cluster, I mean, if you are familiar with some concept of Kubernetes, this is some kind of clusters essentially in the Kubernetes. And each of these computers is considered a node in the cluster. So we have these ones and these clusters, and this data is distributed over them. Each of them, they can do some computations. And then when they are done with their own computation, they can send messages to others. But the total message that they are sending should be at most S bits. And the total message that they are receiving from others, that should be also at most S bits, because that's the memory that they have. And so this is the so at the end of round one, they are doing some computations, and they are have the things that send it to the other computers, and they will repeat these things until at the end we have the results that we want. I mean, the output should be in the computers. Again, that can be in a distributed way, but all of them should have the results. So here we are giving the input, and here we have the results. So we have the input, we have the results, and what is the goal? The goal is to optimize the number of rounds. And so in some sense, we try to optimize the number of rounds. And there is always this trade-off. So this is the main goal. To optimize the number of rounds that we are doing. Why? The number of rounds is the one that takes the most, because this is a communication between computers, and these are distributed. It is a distributed system. Actually, the number of rounds can be quite, each round can take a lot of time. So in some sense, the number of rounds is the main goal that we try to minimize. And at the same time, you need to have this restriction. There is a trade-off between round and the space. Why? So the main goal is to minimize the number of rounds. So minimize the number of rounds. But as I mentioned, there is always this trade-off between round and the space. Because if we can put all of this essentially information in one computer, then we can do everything in one computer, and then the number of rounds would be one. So always we have this restriction on S that we cannot put too much information on each computer. Good. So here I want to just mention some ideas about Apache Spark. That is one of the practical one that is currently used a lot in practice. And some familiarity with that is good. So here, Spark or Apache Spark is based on the fact of distributed datasets. And then this dataset, then you can run programs like Python or Java or others on top of them. So as I described before, so how do we create these distributed data sets? We are reading them. We read essentially the external data. This is from some, you can think about it from any Hadoop file system or something which is compatible with that. Essentially, we will read all the data. Then when we read it, then we are producing this kind of a data set, distributed data set. This distributed data set, each of them would be on different computers. And then we can apply parallel operations to that. The main concept that they are using is based on the building block of Spark is resilient distributed data sets or RDDs. So what is RDD? Essentially, RDD is the same thing that we discussed. It's a collection of elements that are partitioned across the nodes of the clusters. So if we see in the previous case, yeah, so here, as we discussed, these are like each of them is a cluster. Each of them is a cluster, and each of them is a node. So an RDD, this is the data sets. So this RDD is a data set that is partitioned across nodes of these clusters. So this is the data set that can be essentially distributed over all these computers. And cluster, as I mentioned, this cluster generally means the clusters of, you can think about the Kubernetes clusters that can be over several clouds actually. And each of these computers, you can think about also a node. It is actually a virtual server that can essentially operate on this data, and all of them can be operated in parallel. This RDD, as I mentioned, we are just reading the external data. We create this one on these computers. And if needed sometime, we can also ask this Spark to persist an RDD in the memory. This is one model that we call it adaptive MapReduce or massive parallel computation, AMPC, that also somehow use these ideas. But in general, this is a bit more general, this fact that you can ask that some of this RDD be in the memory such that you can reuse them in these parallel operations. Again, AMPC is one particular model that uses this one. But we don't talk that much about it here. One very important thing about this, RDDs automatically recover from node failures. That is super important. One thing which is very important about MapReduce comparing to other parallel things is that these computers that I mentioned, these are all computers that we have it in a cluster. It may happen that one of these computers during this, essentially the operation, it fails essentially. In that case, this is the good things about Apache Spark. So if this one fails, then of course it has some information here. So what will happen? A new computer will come. This new computer will have the same data that this guy had it at this particular round. It starts and essentially takes time to produce some output. Then output, so, and this is the important thing. Of course, this is some kind of asynchronous things that is happening. The output of this data, these other computers might be ready very soon because they are done with the computer. But this guy, because it failed, it could not produce it. The system actually is trying to do in a very nice and distributed way, in some kind of seamless manner, without you understand it. Actually, it waits for this computer as well, or the operations that it can do it, it will do it, such that essentially it brings this new computer into the system, and then use the input of, because this new computer next round, you may want to get some of this data from this guy and some of this data from this guy. So for the others, it may run some of these computers that need to get it from others. So essentially it proceeds as much as possible and waits for those node failure to be recovered, such that the whole system is done in a very nice and seamless way. And of course, it may increase the time that you will get the answer a little bit, but it is done in a seamless way that you don't know even something got failed, essentially. That's the beauty of this Apache Spark, or in general, this MapReduce models, the way that was implemented. That you don't see that there might be some of these nodes. These are the servers. I had like a server. I know that, I mean, once a while it essentially fails. There is some problem goes there. So these nodes may fail during the computation, but you don't see that much. You may see a little bit more delay, but it is essentially seamless because the whole operation system makes sure that, I mean, all the inputs are saved before going to the computer, and all outputs will be also saved when it is computed. And if in the middle of computation something happens, it continues, it brings a new node and essentially continues the operations. That's the beauty of a Spark. It's very, that's exactly this concept of resilient part is coming from this fact. Now, in the RDD API, there are two types of operations that we are doing. So we are doing some transformation. So what are these transformations? Is that you have some data set that you have it. This is a big data set. You may decide that, okay, this data set, I have it on these computers in this way. This one, the first computer, this is the second, and so on. Then I decide to send, then I want to distribute it in a new way. That's exactly this concept of send that we discussed, that I mentioned that each of these computers that are there, they may send some of this information to the others. And this is generally the concept of map. So map, you can consider that when you do the mapping, actually you are sending this information to other computers. There is now, so this is the transformation and the action. So the action is the case that, I mean, when one computer essentially gets all the information, it runs a job on this node. And in general, this is a job that can be run in the whole clusters on each of these individual nodes. So whenever we talk about execute something on a cluster has lots of nodes. Nodes are the computers. So we are doing some jobs essentially on all of these computers. This is typically the reduce by key. Like this is the one typical operation here is the reduce by key. So in some sense, this is mainly the map part is mainly the send part, and the reduce part is mainly the receive part. And the receive and doing the operations on them. So that's the way that you can map Apache Spark essentially with this massively parallel computation model. So in some sense, this is a more general and more simpler model that can capture some of the system operations, system operational functions of Apache Spark, and you can map them together. But in general, whenever you will do the map, in a sense, you are sending this information to other computers. And whenever you are doing the actions or reduce in some sense, you will receive all this information and you will do some action on that. Let me give you one example on these ones. Let me share and then. Good. Great. Okay. So you see the slides, correct?
Yeah.
Great. Okay. So let's see. I mean, see one simple example here that we can run it actually to write the program through Apache Spark. So here, this is a very typical things that actually is a very typical example of use of this kind of MapReduce or Apache Spark. So you are given essentially some kind of big text. It contains lines. So this is a big text. And on each line, you have lots of words. So this is some text file, very big text file that you have. These are the words that you have. Now, one very important operation on that one is that you want to see how many, from each word, you want to see how many of them you have it in this text file. So this is the word count example. Again, this is a big text file is given to you, and then you want to see from each word how many you have in this text file. So generally, this is the one that you can do it. You can, this PySpark is the one that you can use it for. This is actually PySpark SQL, or you can just use a PySpark. So PySpark is the one that has the Spark. You can do it by Python. Now, you will. This is your text file, the one that you want to essentially process it. As I mentioned, that you can read it from some kind of Hadoop supported file system. You will read them. Now, what do we do? This is the whole operations that you are doing. This is one round of MapReduce. So what do we do? First, I mean, in parallel, when you do the map, essentially you are doing in parallel. So you will map this one. Each line you will split. So each line you will take it separately. Again, you can think about that when you are doing this map, everything is done in parallel. So this map, like this step essentially, this map and reduce essentially is done in parallel. So you will just map each line to its words. Then what do you do? Then this is the most important one. This map part, you will each word that you have it, map it into a key and the information. So that's the thing that you mentioned. So for each word, we create a string int pair. What is the string? So if it is like, I don't know, it is say hi is the word, and the int is 1. What do we do for any instance of hi? We are creating such kind of messages. So these are the messages essentially that each of them have the key. The key is the first one, which is hi, and then some information. In this case, just some number 1. So this is a part that each of these computers you can think about that doing in parallel. They are reading these lines. And again, everything is the kind of virtual server. It means that some of these servers actually may run on one computer, but that is something that the operating system and cloud decides about. But anyhow, this compute, you are generating lots of these messages. Each of these computers have part of the text, maybe means several lines. For each of these lines, for each of these words, it generates some of these messages, hi 1. Maybe hi 1, I don't know. The other one is the world, hi world, for example, 1, and so on and so forth. All of this will be generated through these computers, and that there is some load balancing, etc. that it will be done. This is a map part. Now, this is the reduce part. Reduce part, what does it do? This is the reduce part. So you can think about, again, several words may go to one computer. This load balancing will happen. But when you do the reduce, it is the case that all of these guys, that they have the same key, they will go into one computer. So you can think about that each computer essentially processes several of these words, and each computer get all the hi guys, all the hi messages that has been generated for different computers, maybe through this one, maybe through this one. So this hi messages that has been generated through all of these guys, it will come to one computer. Then what does this computer say? It's essentially this lambda is the function that we are defining. It said that whenever you will get 2 of these guys, that they have the same key, the key here would be the word itself, then sum it up the second part. Second part is the count part. So what does it do? So when it reduces, essentially you can think about that. It gets all the highs from different things, and it sum it up all the key parts, all the information part. What was the information? It was essentially 1. So for each word, it just adds 1. What's the result? The result is that for each word, we know how many we have used or how many instances of this word we have seen in this big text file. So that's essentially these 3 operations essentially separate the lines and then all in parallel, and then the word all also in parallel. And then it sends all of them to these guys that are responsible to gathering all these high guys and just sum it up their information. In this case, this number int, and then just count the numbers. And then finally, we will save everything. This is the output that we can also save it in something like some Hadoop supported file system. So that's one round of MapReduce. With one round of MapReduce, you can actually count all of this all the words that is used in a text. And again, if this is a huge text, it might be the case actually this text also is not even in one computer. You may have it in lots of computers. And all of them, this can be done in parallel, essentially. All the lines will be done separately but in parallel, and all these words will be done in parallel. And by this reduce part, we will get the word counts. This can be done very fast. And this is some idea that I wanted to mention about it. This is somehow the thinking between MapReduce, or not MapReduce, massively parallel computations, and Apache Spark, which is one implementation of this model. Any questions so far? Great. So this was one particular example. Now you can. I'm giving a few more examples here. We are talking more about this kind of nice algorithm that exists. And this one was the easy one. And sometimes one round was enough. Not everything is one round is enough. And it would be great if you want actually to get more familiar with this. These are some nice algorithms that you can actually implement them in a Spark yourself and get quite familiar with them. So what is this next problem? So this is the maximal matching. So what is the matching? Matching is just a set of edges in the graph that none of them should share an endpoint. So no such things. So all of them should be independent edge. Generally, we want to find the maximum matching in a graph. So as I mentioned, for example, if you just think about, for example, Uber drivers and riders. So you want to match them. You want to match as much as possible the riders to drivers which are in these areas. One driver might be matched to several riders in around close by neighborhood. But you want to do it in a way that at any time, maximum number of riders are essentially assigned to drivers, because that's the one that you give, essentially make it the system more efficient, and the revenue of the company will goes up. Everything goes up if you can find the matchings. So that's a matching problem. This is one of the matching is an interesting problem that has been obtained by Jack Edmonds in around 1960. He gave the first polynomial time algorithm for matching. And still, after, I don't know, 60, 65 years, this algorithm that has been obtained there is one of the most complicated algorithms that we have for a problem that can be solved in polynomial time. So for problems in P, matching is one of the hardest ones that still we can solve it. And it's interesting that is one of the early problems that early algorithm that has been obtained. I always say that actually Jack Edmonds really deserve a Turing Award because of his contributions. Anyhow, so this is the matching, but the running time of the matching is not, the matching, if you want to get the maximum matching, is not that fast. So because of that, we are considering generally maximal matching. What is a maximal matching? So in general, maximum matching, it means that a matching, say in this case, the number of edges in the graph is maximized. A maximal matching is a matching that you cannot add any more edges to this matching. So this is an example. You can see, for example, here, if you in the graph, you are selecting these just 2 edges. This is the graph that we have it, and we are just selecting these 2 edges. and no other edge. This is actually a maximal matching. So the size of this matching, the number of edges is just 2, because you cannot add any more edges. You see, if you want to add this edge, it intersects with this guy. So we cannot add this one. There's no edge that we can add it. However, interestingly, this matching has a size 3, because there are 3 edges there, but it is not a maximum one. It is not a maximal one. Why? Because I can add this edge. So this is not a maximal matching, but this is a maximal matching. So interesting things that we have it, and we can prove it. We can always say maximal. In general, maximal means locally maximum, but not globally. Here it is the size is 2, is not maximum, but it is locally, we cannot add any more edges. Here the size is 3 and still is not a maximal one. So, but we can prove that the maximal matching has at most half of any maximum matching. In terms of size of that. So the size of any maximal matching, again, the maximal matching may have a different size, but we know any of them has at least half of the size of the maximum matching. Maximum matching, all of them have the same size by definition. Only one can be the global maximum. Maximal, no, you may have a different size, but we know that any maximal matching is at least half of the maximum matching edges. So it is a 2 approximation for the problem. So maximal matching is at least half of any maximal. Maximal matching is at least half of any maximum matching. Good. So that's good things that we know. And now the good thing about the maximal matching is that there is a very simple algorithm for that. So we have this guarantee. It means that it is a 2 approximation. So it's a reasonable thing for practice. And it is very fast. How do we do that? It's very simple. You can see the edges in any order. So the edges of the graph, even they can come as a stream. Anytime that one edge is coming, if you can add it to the matching, you will add it. It's a greedy algorithm. So if you want to find the maximum matching, I mean, this is not such a simple greedy algorithm, but here there's a very simple greedy algorithm. Whenever one edge is coming, if you can add it to the graph, add it. If not, don't do it and just go to the next edge. And this, you can actually do it in any order. So actually a good heuristic to find probably a good maximum matching, if you want to run it, you can just generate random ordering of the edges and just, so you generate a random order of edges and just do this maximal matching algorithm. Again, when they are coming, each edge, if you can add it, just add it to the graph. If you cannot add it, then don't add it. And when you can add it only like if and only if, like for example here, when this edge is coming, we can add it because none of these endpoints are matched before. So that's the condition to be like, it's like a trivial algorithm in some sense. All the edges that are coming, if you can add it, add it. If not, then of course you cannot add it, so ignore it. And again, this is like a good heuristic you can think about that. If you want to even generate a maximum matching, it might be good heuristic to just run a random order on the edges and then run this greedy maximal matching, very simple matching. So this is about the maximal matching. And as I mentioned, this is a very important problem because matching is a super important problem that actually, that makes billions of dollars for these companies like Amazon, Google, Uber. That all of them, they have marketplace. Anywhere that we have, so the matching problem, you can sometimes actually call it a marketplace problem. So it is a super important, like $1 trillion problem, because if you can do it more efficiently, you can match more, then your revenue would be more, and the system would be more efficient. The customers would be happier. That's the important problem. And maximal matching is generally a simple way, because the matching, how it developed the polynomial time algorithm for that is 1960, still is one of the most complicated algorithms that we have it for problem. And this is this algorithm that I have mentioned. The running time of this algorithm is order n, because you only need to do it, go through all the edges of the graph and do that. It is very simple thing that it gives you a 2 approximation for the problem. It's a reasonable things. Other things, if I remember correctly, the running time of the matching is the maximum matching. I think the best one is something like m times square root of n. And here again, m is the number of edges and n is the number of vertices. Good. So we talk about matching. Now let's see how can we solve this problem in parallel. So we want to find the maximal matching. So again, this is all the edges are given essentially on different computers. Like edges essentially, this is some kind of distributed data set that we talk about it in Spark. So your data is essentially distributed over several computers. Each computer has some subset of edges, and say each of them has almost the same number of edges. You want to find the maximal matching of everything. Good. So what is the approach that we are doing? So let's define this one. You are here. We are using this is the approach that is called vertex partitioning. What do we do? And let's define delta be essentially the maximum degree of the graph. How do we want to solve the problem? We want to randomly partition vertices into a square root of delta subsets. Good. So how do we do that? So this is the edges that are on this. So you can consider these are the edges that we have it on different computers. And now, how do we do that? And say here we are assuming that the size of each of this computer can have. So the number of the total size is order m. The number of vertices, and we discussed the number of m can be essentially order n square. Assume that each machine here has order n space. How do we want to solve it? So we will randomly, and this is say this delta is actually the maximum degree. And say for now is the delta can be order n. The maximum degree of a vertex can be order n. How do we do that? We partition this graph, the set of vertices that we have it, into a square root of n clusters. So we will partition them into a square root of n. Say, as I mentioned, say k is equal to delta, which is order n. We are partitioning into a square root of n clusters, or a square root of n sets. And now, each of these square root of n sets, how many edges can have in between? Of course, the size of this graph, this is number of vertices. So this is the vertices. And they can have order n edges. So this square root of n vertices, each of these, when we partition it, they can have order n edges between the vertices of this graph. And the good thing is that when we partition, so how many computers here we have? We say we have a square root of n computers, or as I mentioned here, we are assuming k is equal to order n. But say in general, a square root of k computers. Each of these guys have a square root of, say, at most a square root of n vertices. So the size of the number of edges that will go there would be at most n. Now, so what do so this is the things that we are doing. As you see, so we are just essentially defining these clusters. So in some sense here, how many computers do we need to have? You can think about that. I mean, this is the data that we have it. Each of them, the space on each machine is n. And the number of these guys essentially would be a square root of n. So the number of these computers would be a square root of n, because there are a square root of n machines. And yeah, and this is the data that we have it. So what do we do? We are this is essentially the things that we are doing. That. So we are considering these edges, and we just so yeah, actually the actual data, because each of them can get n. So the total number of computers that we have it here is n, because we need to have n times n, or in general, actually, I will say, let's say. So the number of these guys, so this is the total data on them. So the data, the input data is order m, while the number of them is m over n. So because we have m edges, n computers, so on each of these computers, we can have order n edges. This is the, again, this is the space, which is. So here the space is n. So we have m over n computers or nodes in this cluster of so we have m over n nodes or computer. Each of them have a space n. This is the way that we can essentially keep the track of all these edges, the input. Now, this is for the first round. This is the way that we will read the data from some input data, and then we will put it in this kind of RDDs, essentially, or resilient distributed data sets. Now, for the next round, actually, how many computers we have it here? So for the next round, we only need to have a square root of n computers. And how do we do that? This we have n vertices. Say the number of vertices is 1 to m. We are giving essentially each of these computers. We are to each of these computers. We are sending randomly a square root of n vertices. So each of these computers randomly receive a square root of n vertices. Good. And then how many edges? So, so each of these computers will be responsible to handle a square root of n vertices. So it is, this one is similar, very similar to that word count. Now, any edges which is attached to one of these guys, it goes to, and this is a partition. So we are partitioning the vertices. This is very important. So each vertex goes exactly to one computer. Now, all edges that both endpoints, so if there is one edge here, yeah, so if you have one edge, that both endpoints are in these two, in one computer, we will send that edge to here. So this is essentially an edge AB, where both A and B are here. So any edge will go to one of them. So essentially, it means that all these edges here inside these blue blobs, they are going to this computer. Of course, there are some edges that are between two computers. That one, so this is A, B. A is here, B is in different thing. In this case, in this round, we will ignore them. Good. And what is the goal? We want to find the maximal matching of the whole graph. So if we will just partition these vertices again into a square root of n sets. Each of them have size a square root of n. This can be done in a random way. And then each edge, if both endpoints are belonging to one of this computer, this is essentially, this kind of map and reduce. This is this, it will be sent to that computer to handle it. Good. Now we talk, so this is the way, this is the edges, these are the vertices that have been partitioned. Now what will be the operations that each of these computers, when will do when it gets the input. Each of this computer, when it gets the input, means that all the edges that are attached to all edges induced for this induced subgraph, it just run a random greedy maximal matching on this set of edges. So each of these computers on the set of edges that it has and on the subgraph that it has, it just runs that previous greedy maximal matching. That's the algorithm, very simple things that is doing that. So each computer, so those other guys will be ignored. Only these edges which are in each computer will remains. And each of these computers is just finding a maximal matching, the simple algorithm on the set of edges that it has. Good. Of course, some vertices will be matched. In each of them is a maximal, so each of them is good. The only problem is that what will happen for such edge? So there might be an edge from here. So this vertex is not matched here. This vertex is not matched here, but there might be some edge between them in the actual graph that currently it was ignored because this A and B essentially is in the different computers. Good. So this is the thing that, so in one round, we are just finding each of these guys we are partitioning these vertices. Each edge goes to the each edge, if both endpoints are in one computer, it will be sent to that computer to handle it, or to that node of the cluster. We are finding some maximal matching. So those guys that are matched, we are done. So these guys, these edges that are matched, we are done with them. And we can just essentially keep them as an output. So we know that these guys are matched. The issues are with such edges like this that are between these clusters, and still they can be matched, but we didn't match. So what do we do? So essentially we consider, we remove these guys, and here those edges which are matched, we will keep them. We will save them essentially at the output file to be on some computers, on set of computers to be on the final output. The issues is with the edges that are remaining. Now, what is the idea? The idea is that these edges that remain in this graph, so we have a new graph. Those edges which are matched and those vertices which are matched, you can just actually remove them, both edges and the vertices, from further considerations. So when we remove these guys, then we have a graph that, because we are removing some of these vertices and edges, we have a graph that the degree of each vertex is reduced. So as I mentioned, so we are running this one, and so we are partitioning on each of them. We are finding a maximal matching. And so this is the main thing actually that we want to say. We will, yes, what do we show? We can show that when we do one round of MapReduce, the remaining degree of any, so some of these vertices which are matched and will be gone. Those vertices which are not matched, the degree of these guys goes from delta to minus epsilon for some constant epsilon. Good. If you remember when we discuss this divide and conquer, we mentioned that if you go from n to n over 2, or to n over or n over any constant, essentially the depth of this recursion would be log n. So if you go from n to n over 2, the depth would be log n. Here, we are going from delta to the 1 minus epsilon, or you can think about it, we go from n to the 1 minus epsilon. If in the recursion from a parameter n, you will reduced to instances that in this instance, the parameters n to the 1 minus epsilon or delta to the 1 minus epsilon, the depth of this recursion would be log delta or log. You see, here the reduction is when we go from n to n over 2, it's like linear. Here we are going much, like in each step, we are going much further. We are going from n to the 1 minus epsilon. So it is much more reduction in size. And that's the reason that here we have it log n, and here we have log d. So what is the whole idea? The whole idea is that we can say, because the degree goes from delta to delta 1 minus epsilon, the depth of this recursion would be log delta. And log of n in general is a small thing, but log is almost constant. You can think about constant for almost all practical things, even for very big graphs. It might be a bit larger constant, but it is a constant. So because of this fact happens, the depth of this recursion is exactly the number of rounds. So the depth of this recursion is actually is equal to the number of rounds. So the depth of this recursion is the number of rounds that you can do it. So, and as I mentioned, because the degree of each vertex goes from delta to delta 1 minus epsilon, the number of steps that you have the number of rounds would be log delta. So what's the meaning of that? It means that you will repeat this one. You just divide, partition it into different computers, find these guys at the maximum edges that can go there, they will go there. You want to find the maximal matching. Those edges that are matched and those vertices that are matched, you will just ignore, like save them, and then you will remove it from further consideration, and you will continue with the rest of the graph. You will continue until essentially you are done with all vertices in the graph. I mean, if either the vertices, it would be the case that no edges remains in the graph. So you will continue until no edges remains in the graph. And at that time, you will stop. And the number of rounds would be log delta. And this is like a beautiful algorithm, actually, that we had it like a few years ago. And there were some very much more complicated algorithms there were before. This is a very simple one, actually, that works. And you can easily implement it. And the proof is not that easy. The fact that why the remaining degree goes from delta to the 1 minus, goes from delta to delta 1 minus epsilon for constant epsilon, that's a quite non-trivial things. That you need to actually do lots of probability stuff to do that. I don't want to go to the details of that. I just want to say that there is such a simple algorithm. And again, this has been several previous work was done, and none of them could actually, they mentioned this simple algorithm, but they couldn't analyze it. And we can actually analyze it and get a very nice algorithms out of it. So, and this is one thing that you can do it. And as a result, so this is the paper that we had it in Fox 2019 that actually gets this log rounds for this problem. And actually, so far, this log delta seems the best. We don't know whether you can get anything better than that. This is a very big open problem. Can we get constant number of rounds? We don't know that. But at least we can get log delta for these problems. And that is, log is quite smart. So that was one thing. There are other problems that you can also do it. For example, this is the edit distance or the longest common substring. So this is the edit distance. In general, you want to transform a string S into a string T with the minimum number of operations. So what are these operations? You can add a character. So for example, here character D can be added. So you want to go essentially from S to T. Here you can add a character, you can delete a character, or you can substitute. So for example, here instead of B, you can do D. And say each of them can have, the cost of each of them would be 1. It can be generally, it can be weighted, it can be more than 1. So this is have lots of applications, especially for genetics or any text stuff. this is very similar to the other problem that we talk about longest common subsequence, that when we talk about dynamic programming, we talk about it. You want to find the longest sequence S of that also appears in a string T. And for example, if you have this is S and this is T, you want to find this longest common subsequence. This is like the thing that we have. Now, what is the important thing? So generally, this is the main idea. This LCS plus edit distance is equal to n. What's the meaning of that? This is the main idea. This is somehow complement of the other problem. If you find the longest common subsequence, then the rest of these guys, these are the edges, these are the guys that should be either deleted or inserted to the other things. So the edit distance plus this longest common subsequence, LCS, is generally n, because what you need to do that you will keep these guys and you will delete all these other guys, or you can replace or insert as well. But that's the general idea. If you want to edit it, the best way is to just essentially keep this like insert and delete would be like very similar in some sense, because you can insert one letter from one string or instead add it to the other one. And that's the thing that I mentioned. So you can keep this one and then delete this one. So LCS and edit distance are complement of each other. And there is the same dynamic programming. If you want to do it, you can write it for edit distance. Anyhow, this problem have lots of applications in computational biology, in language processing, and compiler design. And these are very fundamental problems. And for these guys also, the best algorithm for them is for edit distance is n squared. This is the same dynamic programming that you have seen it. LCS, the same thing. And it is actually under some complexity assumption, there is nothing better than n to the 2 minus epsilon. If you remember, we talk about all pair shortest path. There also we mentioned that for all pair shortest path, there is a simple 3 loops Floyd-Warshall that you cannot get anything better than n cube. Here the same thing. You cannot get anything better than, if both of these S and T have length n, or the maximum length is n, you cannot get anything better than n to the minus epsilon. You can shave some polylog, but the polylog is not n to the epsilon. So you cannot, essentially n to the 2 is the best things. And of course, we need to solve this one if these are the very large sequences or large text files. We want to do it in parallel. So that's another thing that actually the MapReduce can be very helpful. And and the idea is that essentially you will put S and T into a set of computers. So S and T, these are big text files, say. You will put them and you want to compute what is the edit distance between these. So you need to do a few rounds and you will compute the edit distance of this. This is essentially the way that we are solving this problem. And you want to reduce the number of rounds. That's the important things. And say here we are assuming that so here we have this one. So this is S. So we have this S and this is T, and say the length of this is N, the length of this is N. And we are assuming that each machine here has size N to the 1 minus epsilon, or N to the minus X. And how many machines then we can have it? We should have N to the epsilon machines. So we have N to the epsilon machines, each of them have size N to the 1 minus epsilon. The space. Now, what is the algorithm? So the algorithm, it would be actually the way that we can do it would be these things. So you compute, essentially this would be the solutions. Yeah. So what do you do? You're essentially, so this is S and T that you have it. So you will put this S and T on different machines. So you can think about these ones. So you have, so this S would be essentially N to the epsilon blocks, each of them size N to the 1 minus epsilon. The same thing for T. This is S, and T similarly. Both of them would be like this. T would be like this again, n to the epsilon blocks. Each of them is n to the 1 minus epsilon. This is the space that each of them. So the number of them would be this. Now, the general idea that, so we will divide essentially this S and T into the epsilon partition again, into the epsilon parts. Then we have machines. How many machines? We have n to the 2 epsilon machines. What do they do? Each of them considers one guy from here, one guy from here. And for each of these, essentially a smaller text, they are computing the edit distance. So each, how many machines we needed? Because here we have n to the epsilon machines to just keep S, n to the epsilon to keep T. Now, for each pair of these sub strings, we have one machines that in parallel, they can compute the edit distance between them. So each of them would be, as I mentioned, so we have n to the number of pairs would be this, and this is the number of machines that we have it. Each of them on this smaller substring, they are computing the edit distance between them. As I mentioned, so this is the things we have n to the 2 epsilon pairs that each of them compute the edit distance for one block from S and one block from T. Then when we compute it, then for all these blocks of S and T, we have essentially the edit distance between them. Then it turns out actually that we have some kinds of super problems. So edit distance, generally you wanted to find between these text of or strings of size n and n. If we are doing that, because in some sense, so between any two pairs of these, so between any two pairs, we know what is the edit distance between them. So we can run another dynamic programming on all of these guys, because we know in some sense we have some super algorithms, because on each pair, I know that if this string and this substring and this substring, what is the edit distance between them? I know that from the computations in the previous things. Then I will consider all of them in, I will get all this information in one machine, and in one step, I will compute the essentially the edit distance between these two super strings, because each strings here is somehow has size n of the original things. So all the solutions are given to one machines, and this one machine compute them by some dynamic programming. As a result, actually, this is another thing that we can get it. So the memory per machine would be n to the 1 minus epsilon. The number of machines would be n to the 2 times epsilon or 2 times x. The round complexity of this algorithm would be 3. In 3 rounds, it can do that. The total running time of this algorithm, the total running time over all machines would be quadratic. And as I mentioned, so in some sense, even though we are distributing, we are not wasting to compute something overlapping and waste in terms of running time. The total running time of this algorithm is quadratic. It means that it is very work efficient algorithms. And the approximations, so we don't get the exact solution, we get 1 plus epsilon approximation for the problem. And actually, getting it exact is a very important open problem. We don't know the answer, but here we can get 1 plus epsilon. That it is for almost all practical instances, it would be very good solutions. So again, this is the algorithm that we had it. We consider S and T, we divide it into blocks of size n to the 1 minus epsilon. Each 2 of them we will give to some machine to compute the edit distance for these 2 substrings. And then when we have this information that for any 2 strings, we know the substring of S and T, we know the edit distance, we can combine all of them to create the solution for the whole S and T in 1 round. So we have essentially 3 rounds, and in 3 rounds, we can get here 1 plus epsilon approximation. So it is very practical and it's a nice thing, and you can actually implement it very nicely in this MapReduce for very large text. So this is 2 problems. Editdistance is a very fundamental problem in the essentially text, like information processing in general. And this other algorithm matching, which is a very important problem for any graph problems or any marketplace problem. And both of them, actually, you can get it much better in parallel. These are very recent results that we had it. And yeah, so we can get a similar result for LCS as well. And good. So I think that's the one that I wanted to cover here. Let's stop share. Yeah, so this is the whole thing that I just described, essentially the whole MapReduce and a few important problems that actually very recently we have a very nice and simple algorithm that you can run it on this kind of big systems like Apache Spark or Hadoop or MapReduce. In particular, Apache Spark is the one that is the most famous one and the most hot topic, and you should know about it for any distributed computing to do it in parallel, such that we can get a much faster algorithms. Good. So if there is no more questions, so thank you all, and we are finishing the lecture now. Bye, everyone.